let's work one problem and go. Let's assume this is A and this is B. We'll say these hit each other such that occur along this plane, along that direction. This is the impact plane. So what we really need to do is find this angle. So we'll say it's a 3, 4, 5. And what I'll do is I'll indicate it with an X. Indicate this one with a Y. Make sure that shows up on the, yep, that shows up, okay. We'll make things a little different this time. Mass of A equals to 1, mass of B equals to 2. Say the velocity of A is equal to 10I. Say the velocity of B is equal to minus. Now, that's incorrect. We'll just, that is I associated with that. So we're just going to say the magnitude of VA is 10. The magnitude of VB is equal to 15. Okay, now, let me see. Here, I'll put up my glasses so I can see over there. And I'll see about right here, all the way up to here. And then right above the, so about right here, this zone up here is where the projector is. So I need to be mindful of that. So what you have to do, you have to break this into components. So we'll focus on this one first, then we'll focus on that one. So here's our X, here's our Y. This is the velocity coming straight up. So I'm going to take it, move it up on top of this. So essentially I'm taking this vector and I'm going to break it into components. So I'm going to put it at the origin. And I'm going to make this go up a little higher. Make this go up a little higher. So this is our 10. It needs to be broken into components along here and along here. I'll have to do this again with this. However, what you'll notice is it is the flipped direction. So I can essentially put the vector there, scale it, so I'll show you that whatever I do here can actually just be translated over to the 15. Now, this is our X. So I know it doesn't look to scale, but it's that. So now, how do I get this vector off onto component here and the component there? A couple of ways. Let's look at it like this. I'll call this theta. Now, if this is theta, I'm going to list a couple things. Now, if this is 4 and this is 3, this distance from here to here is 5. So sine cosine theta 4/5. That, okay, let me break the triangle away. Now, this is that triangle broken away. If you look at the sine, 3/5. Look at the cosine, 4/5. Now, I'll erase that. And now, let's look at these two angles. And the first thing I can say is that angle is not theta, but it turns out these, okay, this is 90 degrees. If I rotate the thing over, that's 90 degrees. I rotated it by theta, so it turns out that's the case. I could call this alpha, but I don't care about alpha. So, here I see it. You know what, since I don't care about alpha, I'll take it back out of there. This being the case, now I can use this information and break down this component and that component. If this is a triangle, this is cosine. Okay, remember this is, let's look at a triangle like this. This is the 90-degree portion. This one would be nothing more than 10 cosine theta. This one is the same one over here. So this one would be 10 sine theta. Now I can take this and say 10 3/5, and I can take this one and say 10, I'm sorry, that should be 4/5. Okay. So that makes this, this and this give me a 2. That gives me an 8. So in fact, VA written in this coordinate. Let me finish this one. This one's 6. VA written in X, Y coordinates would be nothing more than, make sure I do it right, this one runs out the X. That one happens to be 6I, 8J. Now let's take for a second the 15. If I take that vector and move right here, I can do something very interesting. I can say it's minus 15. Okay, now this gives me a 3. 3 times 4 gives me a minus 12. This gives me a 3. Minus 3 is a minus 9. So in fact, on this, I can write VB, which is a vector, which is minus, okay, make sure you get this right. The X component comes first. 9 minus 12J. Now that I've got this, I don't need any of this, and I do need the space over here. So what I'm gonna do is I'm gonna relieve myself of this area and then start working the problem. But these are the initial before impact. We'll be looking at, we're 10 minutes in, so we can easily finish this problem by the time we're done. Let's go ahead and take this off. You can rewind the video, but before I do that, let me make sure the video is streaming properly. Looks like it is. So, let me finish up. It's a little hot in here, so I may speed through and get done. Okay. First, let's work along impact. In this case, the x-coordinate. MA initial, VA initial, plus MB initial, VB initial, equals 2. Now, in the initial to the final state, there was no force external to A and B put on this, so it's just now. I said this was 1, I said this was 2, so it remains 1 and it remains 2. VA initial along the x-coordinate, you just pluck off the x's. So I get a 6 for A, I get a minus 9 for B, and that's what I'm stuck with. So this is 18, looks like minus 12 is equal to okay, so I'm going to box that, and I'm going to save a space, and then under here I'm going to do this. Okay, so coefficient restitution, final, A final minus BB final, sorry for my handwriting, BB initial minus BA, sorry, A initial. Okay, BA initial is a 6, BB initial minus 9. So this goes together with that to give you 15, but it's both minus. So what I'm going to do is write this like this. B is equal to, if this is minus, well, I'll do it one more time. Okay, I'll do it here. And then I'll do it one more time. Take the minus up, swap values. So now I can take this over here, and I can take VB, okay, oh, sorry, it should be a final line. Okay, so again, I took this over to this side, it gives me 15E is equal to that Now what I've done is I've put this one first to line this up. Equation 1 plus equation 2 gives you equals to. These two go away, and then you get 3 VB final. Now, oh, sorry, I wanted to move that over. VA final here, let's see. VA final, VB final, and E, let's do 1.5 and 0. I'm sorry things are a little cramped here, but I'm obviously not going to get all my digits. So if I put in 1 gives me on this left side 15 minus 12, or for E equal 1, I get 3, so I put 3 VB final, and I get 1 here. For E is equal to 0.5, okay, you have to give me a second here. 7.5 minus that, but anyway, let's, okay. Equals to 3 VB final. And E is equal to 0, gives you 12, 3, or, okay, gives you minus 12 equals to 3 VB final, or minus 4. Now, I can take this equation and say the A final is equal to minus 2 VB final. So I'm going to come over here and do that same equation, because then it's both, it's very close on the board. Sorry. So I'm simply copying this, but I'm moving this to the other side because I need to find this column. So I'll multiply 1 times 2, it gives me minus 2, it gives me minus 2, and that's 14. Now we can check stuff in a minute. This time, I'm simply taking this and putting in here. Hang on. Hopefully I haven't made a mistake here. 2 times 1.5. So, if I'm not mistaken, I think I get 15 because this becomes larger. Now it's going to become, oops. I did not do my sign correctly. Minus this. So sorry. And then this time put in a minus 4. Minus becomes plus. That's 8. It'll be 8 minus 12, or minus 4. First thing I see is they both have the same velocity in the impact direction. Second thing I want to check is this one. The way I'll check it, for E is equal to 1/2 MA initial squared plus 1/2, this would be A, 1/2 M B VB initial squared would be 1/2. This was 1. The initial velocity is that. 6 squared plus, now, this came out of this. This came out of that. So, but I'm going to go back to components. Now that's the x component and the y component squared. So in other words, if you're looking at the magnitude, B is equal to Bxi plus Byj. And you want to know the magnitude? It's the square root of Bx squared plus By squared. Now if you square it, the square root disappears. That's what gives you that. Thus, 1/2 mass of B is 2, and it is 9 and 12. Now, give me a second. I'm going to do a couple things here. One of which, let's take this sweater off, because it is extremely warm in here. The second of which is to use the calculator and find the answer to this. Okay. And this, I'm going to go ahead and double check a couple things. First of all, this becomes 100, half of that's 50, plus this. I want to make sure 9 squared plus 12 squared. $225 becomes $275. Now what I'm going to do, before I go on, I'm going to come back here and look at the final states. Okay, the final state, velocity A, velocity of B, equal to and equal to. Now, this is I'm only going to do equal 1 to fill this out. This will be different based upon here, but I'm grabbing these. These, I mean, here, I'm comfortable. These ended up. I'm checking the energy state here. So, VA final. Now, I plus 8J. VB final. This is the X. Remember, this is along the X is where the impact occurs. Now, minus 12J. So notice something here. Not along the plane of impact, or along the Y direction, they maintain themselves. Along the impact direction, they do not. Let's take this over there. Final energy state, 1/2 MA BA final squared plus 1/2 MB BB final squared. 1/2 mass still remains 1. I'm looking at the components. 14. Okay, get the eraser here. Plus 8 squared still 2. I'm taking the VB, which is 1 squared plus 12 squared. Okay, give me a minute here. Okay, clear. This 260 divided that by 2 gives me 130. This, okay, now this is 2.5, so that's just 1, so what I'm looking for is, okay, that's going to be 144, and that's going to be 1, so it's going to be 145. Okay, so plus 145 equals 275. No loss in energy. So this is a way of for us to check the solution here. Now, let's take the worst case scenario. E is equal to 0. That's the case in which the final velocity in the x direction of both of these are the same. I'm going to look at the energy state there to find out how much energy was lost in the worst case scenario. 1/2 the mass of A is still 1. Now, it is not 14, it is -4, or 4 squared plus the original plus 1/2, mass is still 2 over here. This is not 1 anymore, it's 4. The 12 remains the same. So, give me a second. So what you have, I have here 128 divided that by 2. I have 64. This one just becomes 4 squared plus 12 squared, or 160, and it just becomes 160 plus 225. So we lost, remember the initial state, and actually I should not have drawn the arrow to here. I should draw the arrow to there. So we lost 50 units of energy if E was equal to 0. And obviously if you went in here with this one, it should be not 50, but something a little bit different. So that's how you do what they call oblique impacts. This would be something that would occur on a pool table or a hockey table or something like that. So again, let me review this real quick and then I'm going to shut it down. We had velocity specified with a direction. The impact was not along the x or the y, it was off at an angle. I made it like that. Then I went through that little part right here where I broke this into its components along the impact and perpendicular to the impact. That's what you have to do. So once you're along the impact, you use this analysis because you're along the impact. You use this equation and you use the coefficient of restitution equation. I carried it through as a variable. Then I took that equation, stuck right under here, solved them for that set. Created a little table. I guess I could have put the energy here, but if I did, I'd have to go back and fill out the 1/2, and I don't feel like doing that. My key was, when I saw that the velocities along the impact were the same, I felt comfortable that I worked it right. The next one, there's no way to check this unless you go into the energy equation. When you do the energy equation, you do it at final state, and they should match. Now that they matched, I came back and I said, well, what's the worst case scenario? And in the worst case scenario, I looked at the energy there, and that's the energy I lost. So, without much ado, I'm going to call it quits.